Welcome to Homework Lib.
Hi, so in this case we're dealing with this triprotic acid and all of the possible equilibriums that we may encounter. H2A minus, we have also Ha2 minus, and finally we have A3 minus. Of course, all of them with the corresponding hydrogens, but hydrogens that are being left out, for example here, plus H plus, but just to avoid confusion and to do not take all of that space. Let's just simplify this equation as is. So you're told that you have two different solutions containing these two ions because in one of them you have Na2, Ha, and in the other solution you're going to have Na3A. So this means that we are going to employ the Henderson-Hasselbalch equation in order to find the final pH, which is pH equal pKa plus logarithm of the conjugate base with its conjugate acid. In this case, this is going to be concentration of H3 minus divided by the concentration of the conjugate acid, that is Ha2 minus. Okay. So now the other thing that we need to consider is that the final volume, it is going to be 500 milliliters or 0.5 liters. Okay. So now the amount of mole of H3 minus, this is going to be, we have 300 milliliters times the concentration. So 0.3 molar times the volume, that is 0.3 liters. The amount of mole that we're going to have here is equal to 0.9 mole of H3 minus. We could use this quantity in order to get the new concentrations, but I'm going to show you another way to do it in a more efficient way. The other ion that we have is Ha2 minus. The amount of mole that we're going to have from this solution is equal to 0.2 mole times 0.2 liters, and this is 0.4 mole of Ha2 minus. Okay, now we want to get the ratio of the concentrations. So the concentration of H3 minus divided by the concentration of Ha2 minus, it is nothing but amount of mole of H3 minus divided by the final volume divided by the amount of mole of Ha2 minus divided by final volume. Here you can see that the final volumes are going to cancel out in our scenario, so that ratio of concentrations, it is going to be the same as taking 0.9 divided by 0.4. Okay. That is going to give us a value of 2.25. Let me change colors. 2.25. Nice. So now we know that the pH, it is going to be equal to the pKa. Now what pKa I'm going to choose? Well, let's go back to our equation. And the only one where we have a species that are going to be reacting is over here. And the result that we are going to use is a K. In this case, the Ka is going to be equal to 10. Nice. Okay. Now here we could also consider the amount of Ha2 minus that may react with water in order to produce this. Now let's see if that is true or not. So in order to assess if that equilibrium, this express equilibrium, is going to happen or not, we can take the values for the Ka's for each of them. In this case, the pKa it's equal to 10. In this case, the pKa it is going to be equal to 7.5. So this means that the equilibrium it is going to be e to the change of pKa, which is going to give us e to the final, that would be 7.5 minus 10. This is e to the minus 2.5. So this amount for the equilibrium constant in between Ha2 minus and H2A minus is going to tell us that this part we can neglect it. So we can proceed safely with our result. Just for reference, that corresponds to having around, in the case that we only had those two species in solution, that would correspond to having only around 8% of H2A minus in equilibrium. So in this case, that means that we can disregard completely that equation, and we're going to stick with the main equilibrium, that is the one in purple, this one. So after that verification, our problem returns to being simply doing a Henderson-Hasselbalch equation plus logarithm of the ratio of concentrations, that is 2.25. We said that the pKa is going to be equal to 10. So our final result is pH equal pKa plus that logarithm, that is 0.35, gives us a final pH of 10.35. And that will be all for this problem.